It is my honor to introduce Professor Planck, a distinguished figure in construction chemistry, with a PhD in chemistry and over 2 decades of groundbreaking work at SKW Polymers GmbH, where he invented numerous concrete additives and oil-filled chemicals. Professor Planck brings unparalleled expertise to his role as full professor of chemistry at Technical University of Munich. His current research focuses on sustainable binders, polymeric admixtures, CO2 footprint analysis, nanoparticles, 3D printing, and energy harvesting floors. With well over 500 scientific papers, 40 patents, and prestigious awards, including Eisberger Award from CanMed ACI, Professor Planck's impact on the field is immeasurable. So please join me in welcoming Professor Planck.
Thank you very much for a very kind introduction, and I also want to congratulate the organizers and Dr. Kalu for having such a conference, and I certainly encourage you to continue with this. It's the first, and I hope soon it will be the 10th conference. So I think it's a great idea that we have a forum for exchange. And in my talk, I will focus more on the basics of chemical admixtures, and first of all, about some new technologies. But in Europe, very important is the shift in the cement industry away from OPC to what we call blended cements with a low carbon footprint. Cements which we call low carbon or green cements, and this has a big impact not only on the cement industry and the concrete industry, but also on the admixture industry, as I will show in a few examples. But first of all, briefly about our group. I'm coming from Munich in Germany, which is in the south of Germany. We also have some mountains, but not as high as your mountains here in Tehran. And a speciality of our university is that we have close links to the industry. And in the Munich area, there are numerous large and also mid-sized companies in different fields like BMW, which you probably know. And our university had some rather well-known students like Rudolf Diesel, who invented the diesel engine, or Willy Messerschmitt, he invented the jet propulsion. So he made it possible to go from the propeller airplane to the jet airplane. Then our university had 6 Nobel Prize winners so far, and I'm in the chemistry department, and 4 of them, of these Nobel Prize winners, are from chemistry. But about our research, we focus on cement chemistry here, and then admixture chemistry, and this is really our specialty worldwide. I think we are one of the leading groups in this field, and we study the interaction between cement and admixtures, and we also work on other chemical compounds for dry mix mortar and so on. And from the application, it's concrete, dry mix mortar, energy harvesting materials, as was mentioned, and a speciality in our group is we work on additives for oil well drilling, cementing, and fracturing fluids. And I mentioned this before, nowadays students are very interested in IT and artificial intelligence and business management, so how can we attract them into construction? And we had the unique opportunity to do experiments with cement under zero gravity. As you can see here, we performed them on parabolic flights where you have zero gravity. And by the way, this is Dr. Lei, one of my students who is a professor in China now. And we got very interesting insights into the hydration of cement, especially the formation of CSH. Now, this is the context of my presentation. At first, the definition of high-performance concrete, then PCEs for high early strength, and then the big topic, low clinker cement and low cement concrete. Which solutions do we have? One is with ground granulated blast furnace slag. The other is with calcined clay. And then how to optimize the rheology of concrete. Very recent developments in this field and outlook. High performance concrete we define as a concrete which reaches very high early strength within a day, actually ideally within 16 hours, 10 megapascal, and the final strength has to be beyond 60 megapascal, like 100. And at the same time, it should be easy to place, fast flowing, and also easy to pump. And I will talk especially about this because this is not so easy to achieve in such a concrete. And a new requirement is that it should have a low carbon footprint because of a low cement content or a low clinker content. And this is not easy to achieve. Superplasticizers, PCEs, are necessary to achieve this. And at first, a short overview of the PCE technology which we have nowadays. The first PCEs in 1981 were MPEG PCEs based on methacrylic acid and methacrylate ester. Then came the allyl ether PCEs from Nippon Oil and Fats. And then at SKW, we developed the VPEG PCE. And this technology was acquired by BASF, as some of you may know. I framed these two in green because these are still the most widely used PCEs in Europe. In Asia, it's completely different. There, HPEG and IPEG or TPEG PCEs are dominating. They have different alcohol here, as you can see, as compared to those. And very recently, EPEG PCE, which has a ethylene glycol unit here, and GPEG PCE, which has diethylene glycol unit here, were introduced. And I will show you later that EPEG is probably the most effective and cost-effective type of PCE. So as you can see, as this is really very new on the market, the PCE industry is continuously developing further. And although it is 40 years of PCEs, it's by no means finished. Now, the previous speaker talked about water-reducing PCE. Here it shows the structure. This is a high-range water-reducing PCE. It has many carboxylate groups in the main chain and a few but long side chains. And this is a typical composition from HPEG PCE. 89 is the number of EO units here, and 6 is the molar ratio of acrylic acid to the macromonomer. So these high-range water-reducing PCEs actually look like a star polymer. Then a slump-retaining PCE, which is used in ready-mix has many side chains, as you can see here, not so many carboxylate groups, and nowadays we use also hydrolyzing esters in the PCE hydroxyethyl acrylate and hydroxypropyl acrylate because they give super long slump retention. You can reach 3 hour, 4 hour of slump retention. And in some countries like China, this is very popular. Then I mentioned EPEC PCEs, where we have the ethylene glycol unit here. They were, I should say, again introduced to the market in 2019 in China. Oxirang Chem was the first to produce them. And why are they superior? Their production takes only 1 hour of polymerization time versus 3 hours for HPEC and IPEC. And on top, they are also more dosage effective. So this is a very interesting new development. And I'm sure in the industry, over the next years, we will see more and more EPEC-based PCEs on the market. Now I come to a major challenge for the cement and concrete industry, and this is the CO2 emission. When we produce 1 ton of Portland cement, then we release almost 1 ton of carbon dioxide, and therefore the cement industry contributes very much to the CO2 emission and the global warming. And if we look at the list of top cement producers, we see that China is of course #1, followed by India, US, Vietnam, Turkey, and Iran I have here. And Germany, we produce about 30 million tons of cement, so we are a relatively small cement producer. But the total global cement industry produces about 8% of the total CO2 which is released. And by the way, this is more than a country like India releases, so it's really significant and we have to do something about it. What can we do? We can capture the CO2 in the cement plant from the exhaust gas, compress it to a supercritical fluid, and then transport it, let's say, to oil fields and inject them into depleted oil fields. This we call CCS, carbon capture and storage. It's a good way to dispose CO2, but very expensive. It's already done in the North Sea, so we know the cost. The cost is about 80 euros per ton of cement, and this cost will be added to cement, so this will make cement very expensive. The other possibility is that we use pozzolans, as has been mentioned in the presentation before about natural zeolite, and basically reduce the clinker content in the cement by using fly ash, slag, and most recently calcined clay has become very popular. And by doing so, it is possible to become climate neutral with the cement formulation. We need to be below 450 kilo to be climate neutral, and so this is possible. And it means the clinker factor in our cement has to be less than 50%. So for the cement industry, you can see this is a very big challenge and a very big change. Now, cement comes with a high CO2 emission, concrete actually not. Here we have the global warming potential of concrete. It's 130 kilo CO2 per ton or 300 kilo per cubic meter, which is not too high, but the problem is we produce such enormous high volume of concrete, about 25 billion tons, and therefore this large CO2 footprint. And we analyzed the CO2 contribution of different components, and as you can see, cement is 96%. This is where the CO2 emission comes from. The PCE is basically close to zero, not important. So the global cement industry has two ways to reduce their CO2 emission. Concept one is this carbon capture and storage. This allows the industry to keep their current business model, but the cost for this will be very high. And we know in Europe the estimated price for such a cement where carbon capture is done will be above 200 euros per ton. I heard in the days before that the price of cement in Iran is only 2 or 3 euros per ton. So we are so far away, and it shows what a cost burden this technology would bring. The other concept, number two, is to dilute the clinker with reactive SCMs, with reactive materials such as the zeolite. It will keep the cost for the cement low, but it introduces a fundamental change to the current business model of the cement industry, because their clinker will be a minor component in the cement, and the other materials will be the major component. And so for them, it is, regarding the business model, a real challenge. We will see what the future will bring here. Now about slag cements, especially in some countries like Vietnam, India, slags are very abundant, and a lot of work is done. Also in Western Europe, like in UK, France, and we cooperated with some companies on these low clinker cements. You can see we reduced the clinker content to 40%, 30%, 15%, and at the same time increased the slag content. So here you can see the clinker is no longer really a main component, it's the slag. And because the slag reacts relatively slowly, we need an activator, an alkaline activator. Here we use sodium sulfate. And the problem with reduced clinker content is that the strength gets lower. This is the one-day compressive strength, and so we need to find a way to increase the strength, and the most easy way is to reduce the water to binder ratio. But then you have a workability problem, and this is where the superplasticizer comes in. Another example, this is an ultra-low clinker cement with high limestone filler content, and you can see 20% clinker, 20% slag, and a lot of limestone. And if you go to a very low water to cement ratio, you still can get 10 megapascal after 1 day and 60 after 28 days. So with this cement, you have a cement with a very low carbon dioxide emission. So this is, we call it a climate positive cement, which means it reduces the CO2 emission more than what we need, and still we can get very attractive strength data. But the key is the superplasticizer. If you work at this water to cement ratio, you need a very powerful PCE. Some other examples, and this is really what we work a lot on in Europe, these climate neutral, carbon negative binders, like this with calcined clay here. Please make a notice here, it's LC330, which means it has only 30% clinker, the common LC3 has 50% clinker and therefore is not climate neutral. Or a high slag content with 80% slag, or this ultra low clinker cement with 5% clinker, which is something they use in India. And so you see it is possible to formulate very climate friendly binders. Now, a problem with slag cements is we need alkaline activators to get early strength, like sodium sulfate, carbonate, silicate, sodium hydroxide, and we use them in a relatively high concentration, like 2%, 4%, 8% even. And in these activator solutions, normal PCEs are not soluble. And if they don't dissolve in the water, they cannot be active as a superplasticizer. So when we use these binders with these activators, we need new superplasticizers. And Dr. Ley, when she did her habilitation in our university, she was a junior professor there, she worked on IPEC or TPEC PCEs, which dissolve in these activator solutions and are effective. And she found that you need a higher molecular weight and also a higher anionic charge, and then you have excellent superplasticizers even for those systems. Another solution for these slag cements are so-called zwitterionic PCEs, where we incorporate a cationic monomer also into the PCE. And as you can see here, in a slag cement, they give very good fluidity and also very long slump retention, 3-4 hours. So they work very well. The only disadvantage, slight disadvantage, which they have when the dosage is high, that they reduce the very early strength. This is the one-day strength, but after 3 days, there is no such effect anymore. So what I want to say is these new green binders require differently composed admixtures. We have to change the molecules to be effective in those systems, and the PCE industry has many ideas how to accomplish this. Now, calcined clays are talked about a lot, especially LC3. And here you see the LC3 formulation, 50% clinker, 30% calcined clay, 15 limestone powder and gypsum. This has a lower CO2 footprint, but it is not climate neutral. So it's a big step forward, but it is not what we really need to accomplish. And therefore, we are working very hard to improve it. Now, calcined clay, there are different ways to do this. In a flash calciner, it gives the highest reactivity of the calcined clay. In a rotary kiln, maybe this is more convenient, but the reactivity is a little bit less. And very recently, ThyssenKrupp introduced a mill where you take the raw clay and you just mill it. And by milling, you mechanically activate the clay. It's the cheapest way and the most convenient way to have activated clay as a clinker replacement. Now, a commonly known problem of calcined clays is that they require much higher PCE dosages. If we substitute OPC with calcined clay more and more and more, you see the PCE dosage goes up very much. Here we use the HPEC PCE, and especially here where we used a calcined clay from China with a high metakaolin content. If the metakaolin content is high, then this calcined clay needs very high PCE dosage, and obviously this is not very good because it increases the cost. Another problem of such calcine clays, which have a high metakaolin content, is that slump retention is very difficult to accomplish. The previous speaker mentioned this topic of slump retention and that we have different technologies, but all these existing technologies do not work in such a blended cement where we have, let's say, 40% of calcine clay with high metakaolin content. And we and other groups are working very hard on new admixtures which can give reasonable slump retention in those binder systems. Now, what we recommend, if somebody wants to use a calcine clay, we recommend to use a raw clay which has not a high kaolin content, but a relatively moderate, like 10 to 20%. And here we tested such a German clay, which we calcined, and it is from the PCE dosage demand is much better and slump retention is much easier to achieve, but this cement has a slower reactivity. So we need an accelerator to get high early strength in Germany. The one-day strength is very important. The companies always want at least 10 megapascal after one day. And so we designed a accelerator, which is a CSH, a nanoparticle suspension. And as you can see on the data here, it gives more than 10 megapascal after one day, after 7 days, and so on. So with these admixture accelerators, we can solve this problem. Now, let's come to optimized rheology. A big topic in Germany is the stickiness of concrete. And as we go to lower and lower water to cement ratios, this problem, of course, becomes very severe. Here I show a concrete which was formulated with a water to cement ratio of 0.28, and it flows very nice, but very slow. It's sticky like honey, and of course on the job site you don't like this. And we tested different PCEs, like allyl ether PCE gives a much higher flow speed than an MPEG PCE. So the type of PCE already has an influence whether you have more stickiness or less stickiness. But like I said, in Germany, we use a lot of MPEG PCE. So the question was, how can we also improve the MPEG PCE? And the solution we found is if we combine the PCE with a small molecule alcohol, a diol, for example, very simple diethylene glycol or triethylene glycol or PEC 300, some diols, then you improve the flow speed of concrete very much, and even some amines which we use as accelerator work. So by formulating a PCE solution with these simple alcohols, it's possible to increase the flow speed. And the reason is that they reduce the plastic viscosity of concrete. As you can see here, this is without such a glycol. And here we added diethylene glycol. Here we added Jef amine. And then we reduce the plastic viscosity very much. The mechanism is that these alcohols, they do not absorb on cement. They are in the pore solution, and they are a kind of a steric spacer between the cement particles which hold the PCE. And so for osmotic reasons, the particles cannot come too close together, and then we have a dispersion effect. Another possibility to reduce the stickiness of concrete is to use a phosphated superplasticizer, and BASF has introduced this PAE, polyaryl ether admixture, which is a formaldehyde polycondensation product. Here we see phenol, phenol phosphate ester, and a phenol ethoxylate. And by polycondensating, one get a polyphosphate admixture, which works very well at low water to cement ratio and gives a high flow speed. So there are different solutions, and with this I just want to point out our creativity in molecular design enables us to solve such problems. Then self-compacting concrete, it was shown in the presentation before, is very, very common in Germany. In the precast concrete plant, I would say 80% of the concrete produced is self-compacting concrete, and this relies heavily on PCE admixtures and specific formulations, and also on a mixed design, which has been addressed before. And let me show just a short video of SCC. We call it a powder type based on SEM1, fly ash, sand, limestone, aggregate, and a polycarboxylate admixture. This is the J-ring test. You see it has very good flow behavior, no segregation behind the steel bar here. This is the L-box test, and you see no voids, no empty space around these pipes. This is a perfect self-compacting concrete, and here you see how it releases the air itself. So SCC doesn't require much compaction. It is self-de-airing. And this is possible with advanced admixtures. Now, briefly, because of the time, I hope it's okay, thank you, just about some new, very new developments. When we polymerize PCEs, normally we get what we call a random or statistical distribution of the side chains along the main chain. And such a molecule has a limited ability to interact with the cement surface. But if we can make a gradient polymer where we have some blocks of carboxylate groups here, then the interaction is much stronger and we have a more effective molecule. And this is what we have been working on recently to design specific PCE structures in a targeted approach, and we can make molecules now like this, where we have a block of many side chains and very few here, or two blocks of dense side chain, and here no side chain, only carboxylate groups, or these mixtures. And with such targeted design, it is possible to improve PCE performance significantly. Here I show a comparison of different HPEC PCEs with different side chain length. The molar ratio is constant. They are made in the conventional method. These are the dosages which are needed to reach 20 centimeter spread flow. If we make them as a gradient polymer, you see the dosages are about 1/3 lower to get the same spread flow. So these optimized molecular structures actually can make them a lot more cost effective. Also recently we did quite some research on what we call amphoteric PCEs, where we also have a cationic monomer, and there are different ones in the PCE molecule, so not only a carboxylate but also a cationic, and these polymers are very interesting for high calcine clay blended cements, for example, and they also give very high flow speed, as we found in the V-funnel test. Here we had an OPC slag mortar, which we filled into the V-funnel, and the empty time was only 29 seconds with Twitter ionic PCE. The conventional PCE took over 100 seconds, and another reference product took 300 seconds. So, like I said, with these very, very targeted molecular design, we can get very nice specific properties. So this brings me to the conclusion. I have worked over 40 years in the field of chemical admixtures, and at first, I have to be honest, I found it sometimes a little boring with cement and concrete and mortar, but we developed products which were used on very spectacular buildings, and seeing that you create something which really makes an impact on this industry gives a lot of satisfaction. For example, the Petronas towers in Kuala Lumpur were built with our superplasticizers, with melamine formaldehyde-based superplasticizers. Then the Burj Khalifa used our VPEC PCE from BASF, and the Hassan II mosque in Morocco also used the VPEC PCEs from BASF, just to mention a few examples. So if I'm saying this to the young students perhaps here, if you enter this field, you will perhaps also create something where later you can take a look and say, well, we created something really useful, not just a PC program or something which will disappear soon. It has a very lasting effect. Then, I started my work in admixtures in 1980. I joined the company SKW, and my first superplasticizer which I developed was this acetone formaldehyde superplasticizer. This is the original bottle. It was batch number 17 when we were successful, and this is shown in a admixture museum in China now, where they have very interesting exhibits. And at SKW, I was a research director, and we developed these VPEC PCEs, which later became known under the label Master, and the co-worker who did the lab work was Dr. Albrecht, who played a very important role also in the recent development of the EPEC PCEs. And let me show what we have contributed with our PCE. This is the old way of delivering concrete upstairs to a house which is built here, and man, look at these guys here, very strong to throw the bucket with concrete up and to empty a full truckload of concrete. I mean, this is really hard work. By the way, this is a job site in Thailand, and the modern way using PCEs is this. We can just dispense the concrete, the worker can watch it, enjoy a drink, and no hard work, and you see he disposes the bottle in the concrete. That's a modern way of environmental carefulness. And I certainly want to mention our main researchers, our group leaders in the field of PCEs. Here you see Dr. Lei again, and I have a very international group. For example, one student here from Turkey. So because PCE is a global industry, and we strongly believe in the exchange with other groups, other countries. Like here, it's my first time in Iran, and I'm very happy that it was possible, and that actually you invited me to come here, and therefore I only can encourage you to continue with this. Finally, I should mention, because we have a very long tradition in PCE research, in 2015 we started to hold a PCE conference, an international PCE conference, and since then we do it every 2 years. And this year in September, we are going to have the 5th International PCE conference. This time it will not be in Munich, Germany, but it will be in Bangkok, Thailand, because many of our attendants in previous conferences said it would be easier to travel there. It's maybe also cheaper. Munich is an expensive city. And so if you are interested, you are most welcome to join us. We will have really a focus on this industry from, I would say, from the Middle East to Asia, like China, Japan, and so on. So you will see a very international crowd.
Thank you
With
so much.
this, I would like to thank you very much for your patience and for allowing me so much time. And let me say again, what a big pleasure it is for me to be here and to be able to present to this esteemed community. Thank you very much.
Thank you so much. Well, the time is limited, but if there is some questions, just 1 or 2 questions from the floor.
Greetings and salutations, sir. Thank you for your compelling presentation. I just have a question, just wanted to know your own personal opinion on this. Given that there are some materials called dendrimers, which are currently being used in pharmacological industries, do you think that using dendrimers as, again, PCs or other, let's say, performance enhancers might be beneficial somehow to the concrete? Thank you.
Well, thank you. Very good question. About 6-7 years ago, we developed PCEs with dendrimeric structure. They work fantastic, but the cost to, this chemistry is complicated and you need very expensive raw materials. From an academic point of view, we love these, we call them jellyfish-like PCEs because they have these arms like a jellyfish. But I'm afraid the concrete industry is not prepared to pay so much for this beautiful admixture. And this is our situation. When we design molecules, we always have to keep in mind the cost. There are many possibilities, but somebody has to be able to afford it. And yeah.
Thank you, dear professor, for your great speech. Enjoyed it a lot. I have a question about structured PCE. As Dr. Whiteman, I think 5 or 6 years ago from SICA, worked on the block structure of PCE, he showed us that in low summary ratio, it works better. As you mentioned about structured PCE, I wanted to know if there is any new invention about the structure or it's based on Dr. Whiteman researchers. Thank you so much.
Mm-hmm. Yes, you touch a very good and important point. If we go to low water to binder ratios, then the situation in the pore solution is different and the dispersion mechanism changes. In the low water to cement regime, we have what we call a depletion dispersing mechanism, and therefore the molecules need to be adjusted to that. And this is basically what we are doing. And SICA also, I know, had some research projects where they designed new molecules. One was with amine group, in the side chain, this has specific advantages. It makes it a lot more expensive, so on the market you cannot see too much of it, but technically it's a wonderful product.